So what would it take for reality to be understood, for nowhere to exist? Only a bold guess that reality is understandable, and a relentless perseverance to make it such, fueled by blood, sweat, and tears. All while staring straight into the deadliest beast of all, parochial social misconceptions, and fighting back, for there will be a nowhere. Why not you? This was an excerpt from the worksheet of The Fabric of Reality, and today I'll be reading my summary of each chapter with some side notes. The worksheet has 170 questions with answers for you to challenge your understanding and learn main ideas of the book faster. You can find it in the show notes. A little bit about me. My name is Mark, and I'm a 20-year-old who paused university studies to self-educate for a year. In my first 4 months, I've studied David Deutsch, epistemology, quantum physics, computation, and evolution. In the process, I noticed that people take years to understand David's books. This is a problem, and by then I knew that problems are soluble. Hence, I spent hundreds of hours creating a worksheet for each book, and as a gateway into them, the podcast you're hearing now. In the last 8 months, I set out to learn software engineering through MIT and Harvard online courses while doing coding projects on the side. Basically, I took Scott Young's project of learning an MIT computer science bachelor in 1 year and slightly tailored it for my needs. This is my briefest summary with the full story documented on my website. That is markkagac.com. Now, last disclaimer before we proceed. My promise is that we'll cover the main ideas of the book and each chapter, but don't expect a detailed explanation for every conclusion that the book defends. This is the best one can do so briefly, and if you want to dive deeper, the worksheet would be the best place for you to go. And mainly, if you notice any mistake or something I could do better in the worksheets or this podcast, please tell me via comments, Twitter, or email. I treat my critics warmly and respectfully, as they are the only way I could improve. Now, on to the episode. First, we'll summarize the whole book in 5 minutes and then proceed chapter by chapter. To change the world, we must first understand it. To understand it, we take our best scientific theories seriously and jointly. These are epistemology, quantum physics, computation, and evolution. All knowledge creation is a 3-step process: meeting a problem, guessing a solution, and then criticizing it. This is true for art, philosophy, and math. Since knowledge grows through criticism, we can never claim 100% certainty, as we don't justify or create positive evidence for theories, even in mathematics. Science wants to understand the world, which inescapably means explaining it. Prediction is a mean for criticizing theories, not an end on its own. Explanations can't be reduced to fundamental particles, for it is not an explanation at all. Good explanations invoke abstract and emergent phenomena. Knowledge grows both in breadth, number of theories, and depth, scope of theories. The second one is winning. And thus, in the long run, all our theories will converge to one. That would be the theory of everything. It won't be reductive, for good explanations invoke abstract and emergent phenomena. It also won't be our last theory, since knowledge grows through criticism, not justification. As we irreducibly use physical and abstract phenomena in our explanations, they both exist. For whether something is real or not depends on whether it is in our best explanations of the world. Physical world provides a narrow window through which we observe the world of abstractions. Together, they form the reality we are in. Knowledge is a physical force. It can transform the landscape of Earth and much more. The only true constraints are laws of physics. Everything they allow is achievable. The question is, how? Knowledge is the answer. Are things that create knowledge significant? Their significance depends on knowledge power. With the right knowledge, one can bend the universe to their will. Thus, things that create knowledge are universally significant, and thus, life and humans are universally significant. Evolution and epistemology both rely on variation and selection. This is for a reason, as the defining characteristic of life is knowledge creation and knowledge embodiment. To those that seek explanations, quantum physics implies one thing loud and clear:
Reality is far bigger than we ever imagined. It consists of an infinite number of parallel universes which together form a multiverse. Every fiction that doesn't violate laws of physics is a fact in the multiverse. Quantum physics unlocks a qualitatively better mode of computation: quantum computers. They calculate intractable things for classical computers, and one cannot explain how they work without invoking parallel universes. Computation is a process of calculating outputs from inputs by following some rules. Thus, a tree is a computer. Its inputs are air, soil, and sun. By following genetic rules, it is computing its output, growth, and eventual death. Universe is a computer too. Its input is the Big Bang, from which, by following the laws of physics, it is computing its inevitable end. Turing proved there can be a computer that can simulate any other computer. That is, universal Turing machine. Thus, it can simulate anything in the universe arbitrarily well. Universal Turing machine doesn't violate laws of physics, so it is built somewhere in the multiverse, and thus laws of physics mandate their own understanding, and thus laws of physics mandate a nowhere. So what would it take for reality to be understood, for nowhere to exist? Only a bold guess that reality is understandable, and a relentless perseverance to make it such, fueled by blood, sweat, and tears, all while staring straight into the deadliest beast of all, parochial social misconceptions, and fighting back, for there will be a nowhere.
Why not you?
Chapter 1. The Theory of Everything. It seems impossible for someone to know everything that is known nowadays, but is that so? Only if one believes that it is about memorizing the facts. Knowledge is a matter of understanding. It relies on good explanations, not myriad of facts. Good explanations are hard to come by, which is for the best, for only a few must be taken seriously. In this chapter, David refutes instrumentalism and reductionism. He outlines an important thesis of the book. Knowledge grows both in depth and breadth, but depth is winning. Thus, eventually, one theory will encompass everything we know, from math to psychology to literature and so on. That would be the theory of everything. This is the rare case where chapter summary will be just reading David's writing, but this is the best summary he has ever written of his chapters. So here it is. Scientific knowledge, like all human knowledge, consists primarily of explanations. Mere facts can be looked up, and predictions are important only for conducting crucial experimental tests, to discriminate between competing scientific theories that have already passed the test of being good explanations. As new theories supersede old ones, our knowledge is becoming both broader as new subjects are created and deeper as our fundamental theories explain more and become more general. Depth is winning. Thus, we are not heading away from a state in which one person could understand everything that was understood, but towards it. Our deepest theories are becoming so integrated with one another that they can be understood only jointly, as a single theory of a unified fabric of reality. This theory of everything has a far wider scope than the theory of everything that elementary particle physicists are seeking, because the fabric of reality does not consist only of reductionist ingredients such as space, time, and subatomic particles, but also, for example, of life, thought, and computation. The four main strands of explanation which may constitute the first theory of everything are quantum physics, epistemology, the theory of computation, and the theory of evolution. And this was the page 30. Chapter 2. Shadows. In this chapter, David explains the basis of quantum physics, an experiment from which we infer there are parallel universes, and why physicists refer to it as a multiverse. This conclusion is accessible only to those that seek explanations, not predictions. And the summary of the chapter is: light is made out of smallest discrete particles called photons. In fact, quantum physics states that all matter is made out of smallest inseparable particles. Does light travel in straight lines only? On a bigger scale it does, for we cannot see around the corners, but when constrained to smaller sizes, it bends. If you put two slits and shed light from them, you'll get an unusual striped shadows. It's weird, but not disturbing, since we know that light bends on a smaller scale. We can explain the shadows by saying that photons bump with each other like billiard balls, interfering and producing such pattern. What would happen if we sent just one photon? The disturbing part is that with enough time, we'll get exactly the same pattern. But what could be interfering? We can put a detector on each slit that goes off whenever a photon is passing by. Maybe our single photon splits and interferes with itself. Yet, we always observe only one slit going off. So nothing detectable is passing through the other slits. And yet, if we close them, we'll get a different pattern. So something is passing through. We quickly find out that whatever is passing also behaves like light. It penetrates diamond, but not fog. Such results repeat for every other element, not just light. To explain the interference of a singular photon, we must say that there are additional shadow photons traveling with it that we can't see, yet they impact the one we can see. As the same is true for other elements, we say there are additional shadow elements for everyone that is visible to us. Elements and photons together form a universe, a parallel universe. Chapter 3. Problem solving. Claiming the existence of parallel universes is a radical worldview from any perspective. How do we know? How do we arrive at such conclusions? These questions are studied under epistemology, the main focus of this chapter. In this chapter, David explains why inductivism is false and what the true process of science is, Popperian epistemology. He also touches upon solipsism, which we'll discuss in detail in the next chapter. And the summary of the chapter is: empiricism is a philosophical view that we derive knowledge from our senses. It is wrong, for it doesn't explain how we choose what to observe. There are infinite things to look at. We can't observe all at once. Solipsism is a set of philosophical theories that say reality has some boundary, like matrix, or that it is all a dream happening in our head. Induction says that knowledge is created by pure observation and extrapolation of those observations. Observation can't be pure, for it is a mistake of empiricism. But the other problem is that it tries to justify theories by doing more observations. This is bad, for the same observation can justify diametrically opposite theories. Popperian epistemology comes to replace both empiricism and induction. It says that all knowledge creation is about problem solving. You guess a solution to the problem and then criticize it, not try to prove it right. Moreover, all our observations are based on our theories, so that solves the empiricism problem. Finally, since all knowledge is just a guess, and observations are based on our theories that can be wrong, all knowledge is fallible. We can never have 100% certainty about anything, even that 2 plus 2 is 4, for we use our brain that is fallible. Popper claims we never create a positive evidence for theory, like in induction. We can only criticize it. Chapter 4. Criteria for reality. When arguing for the multiverse worldview, we have inexplicitly rejected a set of solipsistic theories, while subscribing to realism. It is time to test that assumption, and the summary of the chapter is: realism is the view that reality objectively exists, regardless of a subjective observer, meaning the chair you're sitting would still exist, regardless of you looking at it or not. Solipsism is the view that there is some boundary to reality, like that it is all a matrix or a dream in your head. It is hard to disprove, for every prediction it makes would also be in line with realism. So how do we distinguish the two? Through a philosophical argument. Solipsism is wrong because it is easy to vary. It has one needless assumption that it's all just a dream or a matrix. This assumption is easy to vary, so we can fill in the blank whatever we want, like it's a matrix with two computers, not one. The second one is running specifically for Chinese due to their firewall. Or we can say three computers, and so on. The same way, we can distinguish between heliocentric, the theory that Earth moves around the Sun, and geocentric, the theory that everything moves around the Earth. Geocentric theory makes a needless assumption that it's easy to vary. Yet, with heliocentric, remove one node and harmony will fall. Something is real or not if it is in our best explanations of reality. Chapter 5. Virtual Reality. David explains that the human brain is like a virtual reality machine because we can render environments both real and imaginary. Our perception of the world is a virtual reality created by our brain from its sensory inputs. Understanding involves comparing our reality with the external one. Through scientific method, we can improve our accuracy. This analogy makes it obvious that our reality is always fallible and inaccurate, for we don't receive it from some ultimate source. It is just our senses and guesses. The main question of the chapter is, what, if any, are virtual reality ultimate limits? What sorts of environments can in principle be artificially rendered, and with what accuracy? In principle, I mean, of course, ignoring transient limitations of technology, but taking into account all limitations that may be imposed by the principles of logic and physics. Page 103. And the summary of the chapter is: virtual reality machines can render logically possible external experiences. They can't factorize the prime number, nor give you a feeling that they did, for it would be an internal experience. Interestingly, the accuracy of a rendering can be perfectly accurate, since we just need to figure out how to simulate people's brain nerve. Thus, in principle, virtual reality could simulate any experience and emotion a person could ever feel, as accurately as we experience the real world itself. But how could we know whether something is a virtual reality or not? Laws of epistemology are universal, so we can find out only by disproving a virtual reality, never proving it. Science and virtual reality rendering is the same process. Both are interested in simulating the physical world as accurately as possible. Thus, science is about getting a more accurate rendering of physical reality in one's brain. Einstein had a more accurate rendering once he discovered general relativity. Before, his brain was running on Newtonian physics program. What do we mean by it was running on Newtonian physics program? Our perception of reality is based solely on electrical currents in our brain, yet we never experience them. So what do we experience? A rendering of reality that is done by our brain based on those currents. When we read symbols that represent Newtonian physics, we are imagining what they mean, and we are updating our view of reality. From then on, we are executing Newtonian physics. Its code are symbols. Chapter 6. Universality and the limits of computation. David explores what are the limits of virtual reality machines. He claims that it is possible to build a virtual reality generator whose repertoire includes every physically possible environment. Hence, reality is comprehensible. Quote from page 123. The heart of a virtual reality generator is its computer, and the question of what environments can be rendered in virtual reality must eventually come down to the question of what computations can be performed. The chapter's main question is, and this is at page 123 again, is there a single virtual reality generator, buildable once and for all, that could be programmed to render any environment that the human mind is capable of experiencing? And its summary is, to build a VR that simulates any physical environment, we must start with the speed and memory constraints. David addresses speed by giving the machine ability to pause human mind until it computes the next steps. By definition, user would have no feeling of the pause. Memory is tackled by having a mechanism that adds and replaces memory disks. Would this machine then have the repertoire of every physically possible environment? No, for they would have to be encoded in memory for the program to run, and the best case scenario, this is an numerable infinity. Yet, a set of every physically possible environment is not a numerable infinity. The latter is bigger than the former. What is the difference? Can one infinity be bigger than the other? It can. We know it because of the Cantor's argument. It says that a set of positive integers like 0, 1, 2, 3 is smaller than all real numbers between 0 and 1. The difference is simple. You have a starting point from 0 with positive integers, while you don't with numbers between 0 and 1. Where do you start? At 0.0001? Or maybe 0.000001? You can always add zeros. Thus, when we compare infinities, by doing a one-to-one correspondence, we can't even start with the numbers between 0 and 1. So it is bigger. David doesn't get upset and rephrases the question to, can we have a VR machine that has the repertoire of every other VR machine? The answer is a resounding yes. Turing thought of a simple machine that only writes zeros and ones on a piece of paper. He then proved that it has the same repertoire as any other machine of that kind. This is called the universal Turing machine. Computation is calculating an output from input by following a number of predefined rules. A mathematician is doing a computation. Hence, whatever he is doing can be done by the universal Turing machine. Universe can be seen as a computer too, calculating the output by following the laws of physics. Hence, universal Turing machine should be able to arbitrarily well simulate it. And if it is physically possible, it must have happened somewhere in the multiverse. Thus, laws of physics mandate their own comprehensibility. Chapter 7. A conversation about justification. David explains the modern problem of induction and how this is not a problem at all. Inductivists search for the justification of the theory, but all our knowledge is just a guess, some better than others. There is no way to justify the guesses we make, only to refute them in search of the better ones. And its summary is, the modern problem of induction is that humans don't understand how can we prefer one theory over the other if we don't have a positive evidence for it. Since I can create infinite number of theories, variations, how could I choose between them? For example, I make up a Mark-float general relativity theory. Everything is just like in general relativity, but when I jump from high places, I would float instead. Assume we follow Popper and test the theory experimentally. I jump from a high place and unsurprisingly ascend and die. Could we disprove such theories without experimental test? For if we can't, then I can make up an 8 billion different versions of the general relativity for each human on Earth. Why do we trust the original general relativity over its infinite counterparts? The absence of a good explanation for this choice is the modern problem of induction. It has a few other traits, and I'll leave them out for brevity. We have seen a similar problem before in the criteria of reality chapter. The answer is the same. Refute all those 8 billion theories, for they add a needless assumption that is easy to vary. But general relativity, in its original view, is not. Chapter 8. The significance of life. How do we know whether something is alive or not? On the first glance, the answer seems to be in genes, i.e. the replicating molecules. But when questioned closer, we understand that the true universal premise is about knowledge. What are the implications on the universe of this idea? You'll find out in this chapter. And the summary is, molecules are the basis of life. A replicator is something that causes an environment to replicate itself because it can't do it on its own, like a song or a molecule. Replicator molecules are called genes. Genes' environment is called a niche. Some niches are more suitable to genes than others. The more gene replicates in a niche, the better it represents some fundamental knowledge about the niche. Song can only be replicated by people. The more viral song is, the better it embodies some profound knowledge about the people that listen to it, that is, replicate. A popular misconception is that all organisms are replicators. David says this is false, and molecules are the only one that get actually replicated. And as a side note, I challenged this idea in the worksheet. Now moving on. Virtual reality is related to evolution, for they are doing the same function. Both are trying to embody some profound truth about the environment they're in. If they do the job poorly, they are discarded. Virtual reality is trying to be as accurate simulation of the real world as possible, while genes are trying to replicate as much as possible. However, replication cannot be the essence of life, for I can imagine a species that doesn't replicate but tries to preserve itself by constant maintenance. The better it is at adapting to the environment, the more it will survive. And as a side note, I challenge this idea, as there would be an evolution of adaptation of ideas within that being. But all of this in the worksheet. Moving on. So what is the basis of life? It is in the embodiment of knowledge about the entity's niche. Moreover, as life seems to be the only thing that creates knowledge, it is the means through which the strongest version of the Turing principle becomes reality. And the principle is that it is possible to build a machine that arbitrarily well simulates reality itself. Humans and life are significant, for they are the only ones that create knowledge. Knowledge has an immense bearing on what the universe will be in the long run, just as it had impact on how the landscape of our planet looks like. And thus, humans are cosmically significant. Chapter 9. Quantum Computers. The questions that we answer in this chapter are: what are quantum computers? What tasks they can do better than classical ones? How is chaos theory disproved by quantum physics? Why quantum physics is random for us but deterministic objectively? And the answer to those questions and the summary of the chapter is: a quantum computer is a computer that uses other universes to perform parts of its computation. It then assembles their results with its own and gives the final answer. This makes it significantly faster than any other classical computer. Computation complexity theory studies how efficiently, in principle, a task can be done. A task is computationally intractable if time to perform it increases exponentially. Many intractable tasks for classical computers are more than tractable for the quantum ones. Chaos theory says that a butterfly can cause a hurricane, but this is only in classical physics. It says so because in classical physics, things are unpredictable because they can never measure things accurately enough, for everything is continuous, so you can always improve accuracy. And as you simulate the model, small deviations in measurements produce wildly different results. But reality is quantum and matter is discrete, so we can measure things sufficiently accurately. Butterflies don't cause hurricanes. What happens is that we subjectively perceive hurricane or not, but in the multiverse, both scenarios have played out. Since butterflies are so small and inconsequential, they don't impact the measure across the multiverse of hurricanes happening. Say it's 50-50 and with butterfly it stays around the same 50-50 but maybe with minor deviation. Thus, this is why quantum physics is subjectively random for us, as we observe only one scenario happening, while objectively it is deterministic, as all scenarios will play out. Shor's algorithm is a program that runs on quantum computers to do factorization of very large numbers. It is intractable for classical computers, and all our modern security is based upon it. If there are no parallel universes and multiverse is wrong, where Shor's algorithm is performing the computation? The atoms in our visible universe wouldn't be enough for it? Where does it take the resources to compute things on? The answer was long obvious to those that seek explanations of the world. Parallel universes. Chapter 10. The nature of mathematics. In this chapter we explore several questions. Do abstract entities exist? Like the idea of a perfect circle. How do we learn about abstract entities if no one has ever saw them? What is Gödel's incompleteness theorem? What implications it has for mathematics? Does Euclid's axiom that triangle is 180 degrees hold in reality? And its summary is, abstract entities exist. They are abstract for they don't have a physical representation yet, like a perfect circle or the next highest prime number that is currently not known to us, but we are actively searching for it. Something exists as long as it is a part of our best explanations of reality. Math, perfect circles, next highest unknown prime numbers all exist. Just as with any knowledge, we learn about abstract entities through guesses and criticisms of those guesses. In science, we criticize experimentally. In mathematics, proof plays that role. Laws of epistemology are universal, and they apply to our knowledge of math as well. If we have proven something, do we know it with 100% certainty? Of course no. Our brain is fallible. We use it to learn about mathematics, so even if we have proven something, we could always be mistaken. We could always have had misfirings of neurons which caused us to believe one over the other. Yes, it is very unlikely, but it doesn't subtract from the fact that it is possible, so we can't claim 100% certainty. Mathematics had crises for they couldn't agree what is the source of knowledge of mathematical entities. They struggle to understand how we learn about perfect circles without ever seeing one. They are, of course, making an empiricist mistake. We don't need to observe anything. We always use our creativity to create knowledge, be it about stars or circles. Hilbert wanted to solve the source problem by creating a number of fundamental mathematical inferences so that every proof could be reduced to them. To everyone's surprise, Gödel proved it is impossible. This is of course obvious when one thinks of mathematical knowledge the same way as of any other of our knowledge. Of course, there is no rigid algorithm for creating knowledge, as it is always a creative process. One can't just follow a recipe. For the reason one, mathematics is a study of the absolutely necessary truths, even independent from the laws of physics. But one never gets such certainty as a reward, for we always use our fallible brain. The worksheet and this podcast won't have chapters 11 and 12, for I would want to wait for Brett Hall's breakdown of those chapters, and they're also not crucial to the main physics of the book. So we're moving on to chapter 13, the Four Strands. This chapter is a bit all over the place, but the main questions we tackle are: what is Kuhn's philosophy, and what is its criticism? What are the basics of rationality, and how quantum physics explains free will? And the summary to the chapter is: Kuhn explains science in paradigms, a set of beliefs and theories that generations of scientists hold. They are imprisoned in those theories and don't change significantly one's opinions. Openness to criticism, non-authoritative values are all myth. Once the evidence for the opposite theory accumulates, new generation of scientists begins to embrace it, mostly for selfish reasons, as they would rise with new ideas succeeding. Past generation is no better, as they hold on to past theories for the same selfish reasons. Moreover, this theater of selfishness is for nothing, as no one paradigm is objectively better than the other. They're all relative, and all the fuss was for nothing. No real progress is ever made. Obviously, Kuhn is wrong, for claiming that science makes no objective progress is nonsense. General relativity not only makes objectively more accurate predictions, but also has objectively better explanations of reality. Kuhn's entire philosophy is more likely to be associated with his own field of sociology and his own frustrations with it, not of all sciences. Pragmatic instrumentalism is a variation of instrumentalism making the same mistake of disregarding the explanatory power of theories. The essence of rationality is taking good explanations seriously and not discarding them lightly. Individually, all four theories of this book have explanatory gaps and are reductive. Yet, if one takes them mutually and seriously as explanations of reality, a mesmerizing, far more complete framework of the world is presented. Chapter 14: The Ends of the Universe. A big part of this chapter is centered around the omega point idea. David, in the beginning of Infinity, writes that such theories have been ruled out. Quote, beginning of Infinity, page 451. A small part of the revolution that is currently overtaking cosmology is that the omega point models have been ruled out by observation. Evidence, including a remarkable series of studies of supernovae in distant galaxies, has forced cosmologists to the unexpected conclusion that the universe not only will expand forever, but has been expanding at an accelerating rate. Something has been counteracting its gravity. And that's the end of quote. Nonetheless, it is still useful to analyze David's hypothesizing. It is a great example of David taking an idea seriously and letting its implications fully play out. If we want to understand the world, we must have the courage to take our best scientific theories very seriously, and we must have the boldness to uncover their implications. This is a perfect illustration of such intellectual bravery and boldness. The essence of this chapter is whether laws of physics impose an upper bound on the computational steps in the universe. If not, knowledge creation could be an infinite process. Even though a megapoint theory was ruled out, dark matter, the thing that might counteract gravity, could imply infinite computation in some other way. For now, we don't know. And the summary of the chapter is: knowledge indeed is growing both in depth and breadth, but depth is winning, so will eventually converge to a single theory of everything. That would be only the first theory of such kind. It wouldn't be a unified theory of fundamental physics, and emergent phenomena would be left unexplained. One should consider our best theories of reality both seriously and jointly, that is, quantum physics of the multiverse, Turing's theory of universal computation, neo-Darwinian evolution of theory, and Popperian epistemology. It takes bravery and boldness to unravel what our best theories of the world imply, as you'll have to face the enemy of all progress, imprisoning parochial social conventions.